Welcome to Module 4, where we explore object-oriented programming, the foundation of modern, professional-grade Python. Instead of loose scripts, we will learn to bundle data and logic into classes to model real-world concepts. Welcome to Lesson 5, Polymorphism, one method name that produces many behaviors, where the same call adapts to whatever object it is working on. You already glimpsed it in the capstone, when withdraw behaved differently per account. Now we will make it explicit. Polymorphism is what lets you write general code that works across many types without caring about their specifics. The word breaks down cleanly. Poly means many. Morphism means forms. Many forms behind one name. The remote control analogy says it best. One power button, but its effect depends on the device. It turns on the TV, cools the room with the air conditioner, or plays music on the sound system. Same action, different behavior, decided by the object receiving it. That is polymorphism. One interface, many implementations, which keeps code flexible and easy to scale. Here it is in code. 3 unrelated classes, dog, cat, and bird, each define their own speak method. The loop is the key. It calls animal.speak, without knowing or caring which type it holds. Each object responds in its own way. Notice we did not even use inheritance here. In Python, if objects share a method name, they are already polymorphic. This duck typing is central to Pythonic design. If it has a speak method, you can treat it like anything else that speaks. Polymorphism pairs beautifully with inheritance. Here, animal defines speak, and dog and cat each override it. In the loop, we treat every object as an animal, yet each runs its own overridden version. That is the mechanism. Overriding a parent's method in each child is how inheritance produces polymorphism. The calling code stays completely generic, it just says speak, while the write behavior fires automatically for each object. This is the pattern you will use constantly in real systems. 2 more angles. On the left, circle and square each define area, and one loop calls it across both. The same polymorphism pattern with shapes. On the right, something you have used all along. Len works on strings, lists, and dictionaries alike, returning the right length for each. That is built-in polymorphism, one function adapting to many types. Python's whole design leans on this, which is why the language feels so consistent to use. Your turn. Create car, bike, and plane classes, each with a move method that behaves differently, driving, riding, or flying. Then put them in a list and call move in a loop. Try it before revealing the solution. The solution shows the now familiar pattern. Shared method name, different implementations, one loop treating them uniformly. If this feels routine now, polymorphism has clicked. Recapping polymorphism. It means one method, many behaviors. Different objects can share a method name, a loop can call that one method across many objects, and the program need not know each object's type. Method overriding is how inheritance creates polymorphism, and Python ships with built-in examples like len. The payoff is flexible, clean, scalable code. Next, we will apply this in a real payment system. Let us put polymorphism to work in a realistic scenario, a payment system. Modern checkouts accept credit cards, PayPal, cash, and more, yet the checkout code should just say pay, and let each method handle itself. That is polymorphism, solving a genuine engineering problem, and it is the kind of design you will meet in real e-commerce systems. Here is the design. A payment base class defines the shared interface, and credit card payment, PayPal payment, and cash payment are children that each implement pay their own way. Why does polymorphism fit so well? Every method does the same job, process a payment, but each does it differently. A single pay call works for all of them, and, crucially, adding a brand new payment method later never forces you to rewrite the existing code. That is the open-closed principle in action. The code makes it concrete. Payment defines pay as a common interface, and each child overrides it with its own message and logic. On the right, we drop different payment objects into one list and loop over them, calling pay on each. The loop is completely blind to the specific types. It just trusts that every payment can pay. That is polymorphism giving you clean, uniform processing across diverse objects. Now watch the real power. We add a brand new bank transfer payment class, append it to the same list, and the existing loop handles it with 0 changes. The output shows all 4 payments processed uniformly. This is why polymorphism matters in production. Your system grows by adding new classes, not by editing working code, which dramatically reduces the risk of breaking what already ships. That is professional, extensible architecture. Our final pillar is abstraction, hiding the messy internal details and exposing only what the user actually needs. Where encapsulation is about protecting data, abstraction is about simplifying the interface. Together, they let you build components that are both safe and easy to use. This is the concept that ties the whole module together. Abstraction means hiding complex implementation and exposing only the essentials. The car analogy is perfect. You drive using the steering wheel, the pedal, and the brake. A simple interface, without knowing anything about the engine, fuel injection, or gearbox underneath. You interact with what the object does, not how it does it. Good software works the same way. Expose a clean, minimal interface and hide the machinery behind it, so users focus on their task, not your internals. Python formalizes abstraction with the ABC module. Importing ABC and abstract method, we make payment inherit from ABC and mark process underscore payment as abstract. This does two things. It declares that payment is a template not meant to be used directly, and it forces every child to implement process underscore payment. Trying to create a payment directly raises an error. Abstract classes let you define a contract, a guaranteed interface, that all subclasses must honor. With the contract defined, each concrete class fills in the details. Credit card payment and PayPal payment both inherit the abstract payment and provide their own process underscore payment. Because the parent demanded it, every child is guaranteed to have this method, so the code that uses them can rely on it completely. If a child forgot to implement it, Python would refuse to create that object. That is abstraction enforcing consistency at the language level, not just by convention. Why abstraction helps? It reduces complexity by letting you work with simple interfaces instead of tangled internals, and it produces cleaner, more maintainable code with clear responsibilities. 2 rules to remember. First, you cannot instantiate an abstract class. Payment errors, so you always use a concrete child. Second, children must implement every abstract method. Skip one and Python raises an error. These guarantees are exactly why large teams rely on abstract base classes to keep code consistent. Here is abstraction in a small store system. Payment is abstract with an abstract pay method, and credit card, PayPal, and crypto each implemented. The loop processes all 3 uniformly, which is polymorphism riding on top of abstraction. Notice how the 2 pillars complement each other. Abstraction guarantees every payment type has a pay method, and polymorphism lets one loop call it across all of them. This combination is the backbone of extensible real-world systems. Recapping abstraction. It hides complex logic and shows only the essentials, so you use what an object does, not how. The ABC module provides ABC and abstract method. Abstract classes cannot be instantiated directly, and their abstract methods must be implemented by every child. The result is reduced complexity, better structure, and a consistent interface across classes, the same technique used in payments, authentication, storage, and databases. That completes all 6 pillars. For our final project, we combine all 3 advanced pillars, inheritance, abstraction, and polymorphism, in a single employee management system. This is the payoff of the whole module, seeing how the concepts do not just coexist, but reinforce one another in real software. Watch how each pillar plays a distinct, necessary role. The scenario. Model a company's staff. Every employee has a name and an ID and must be able to calculate a salary, but each type calculates it differently. The design uses an abstract employee base with full-time, part-time, and contract children. Here is how the pillars fit. Abstraction sets the rule that every employee must calculate a salary. Inheritance shares the common name, ID, and display logic. And polymorphism runs one calculate underscore salary call across every type. 3 pillars, 3 distinct jobs. Here is the structure. The abstract employee base handles the shared constructor, name, and ID, and provides display underscore info, while marking calculate underscore salary as abstract so every child must define it. Then the 3 children each implement calculate underscore salary in their own way. Full-time returns a fixed monthly figure. Part-time multiplies hours by rate, and contract returns a flat amount. Each child calls super underscore underscore init underscore underscore to reuse the parent setup. Inheritance, abstraction, and the seeds of polymorphism, all in one clean hierarchy. Now we run payroll. We build a list holding one of each employee type, then loop once, calling display underscore info, and calculate underscore salary on every employee. That single calculate underscore salary call returns the correct figure for each, 5,000 for full-time, hours times rate for part-time, a flat amount for contract. One loop, many salary formulas, 0 type checking. This is the 3 pillars delivering their combined value. Uniform code that handles diverse behavior effortlessly. Here is the architecture summarized. Abstraction is the rule. Employee forces every type to define calculate underscore salary without dictating how. Inheritance is the shared code. Each type reuses name, ID, and display underscore info. Polymorphism is the one call. A single calculate underscore salary returns the right result per employee. To extend it, add intern or manager types, yearly bonuses, total payroll sums, or formatted payslips. Because the design is clean, every one of those additions is straightforward. Congratulations, you have mastered all 6 pillars of Python OOP. Classes and objects, methods, encapsulation, inheritance, polymorphism, and abstraction. Together, these form the foundation of professional Python. Every serious application you will build web backends, data pipelines, games, and machine learning tools, is made of classes working together. The best way to cement this is to keep building. Take the projects from this module and extend them, then start modeling problems of your own in objects. Well done. Here is our roadmap. We will master classes, objects, methods, encapsulation, and inheritance. We will finish with a capstone project that extends into polymorphism and abstraction. Each lesson builds directly on the previous one. Let us begin with the two most fundamental ideas in OOP, classes and objects. A class is a blueprint, and an object is a concrete instance built from it. This mental model is the core of everything we will build. Think of a class as an architectural blueprint. An object is the actual, independent realization of that blueprint. Every object carries data in attributes and performs actions using methods. This is the simplest class. Class dog, pass. Even empty, it is a usable blueprint. Creating objects like dog1 and dog2 results in distinct instances at different memory addresses. To make objects useful, we use the underscore init__ constructor. It runs automatically when an object is created, initializing its attributes. Notice how dog1 and dog2 hold different data, despite sharing the same class. The self parameter is a reference to the specific object currently being operated on. Methods are functions inside a class that use self to access and manipulate that object's unique data. When we combine multiple attributes and methods, as seen here in the student class, we create powerful, reusable units. The object knows both what it is and what it can do. Here is a practical application, a bank account class. It maintains a balance and provides deposit and withdrawal methods. The object remembers its state across these operations, demonstrating how state and behavior are linked. Why use classes? They help you organize, reuse, and scale your code effectively. Remember to use Pascal case for class names like student or bank account to follow professional naming conventions. Here is a mini exercise to test your understanding. Try building a book class with a title, author, and pages attribute, and a display_info method. Pause the video and try it yourself before moving on. This student management system is a great way to reinforce these concepts. Defining a class, assigning attributes, and building methods is a pattern you will repeat constantly in your projects. We have covered the essentials: definitions, constructors, attributes, and methods. These are the building blocks. Everything coming up will be an extension of these core concepts. Next, we will focus exclusively on methods. We have seen the basics, but now we will dive deeper into how they return values, accept parameters, and interact with each other. To recap, a class is your blueprint, an object is your instance, and methods are your verbs. Always consider what actions your object should perform, and turn those actions into methods. Let's explore methods, which are the actions your objects can perform. The simplest method is defined within the class and takes the "self" parameter, which refers to the object itself. When you call a method like my_dog.bark, Python passes the object as self behind the scenes. Knowing this makes self easy to understand. It's simply the object acting on itself. Methods become truly powerful when they interact with data. You can use stored state via self or accept external input using method parameters. For instance, a dog can use its name stored in self to bark, or a calculator can take two parameters to add numbers together. It is about blending stored state with flexible input. While printing results to the screen is fine for simple scripts, professional code typically returns values. Returning lets the caller store or reuse that result later. Consider the bank account class example. By adding multiple methods like deposit, withdraw, and check balance, you create a complex, capable object in one place. Objects can also call their own methods through self. This creates modularity, keeping individual methods small and focused, which is a hallmark of good class design. Take this user system example. Login and logout are separate, focused actions that make the code easier to test and maintain compared to a single monolithic function. Follow best practices. Use descriptive, verb-based names, keep methods small, and prefer returning values over just printing them. Avoid beginner traps like forgetting the self parameter in your method definitions, or trying to call a method directly on the class rather than the object. Now let's apply these concepts. In this shopping cart project, you can see how several methods cooperate to manage a list of items, demonstrating how state and behavior link. This concludes our deep dive into methods. We have covered definitions, parameters, return values, and composition. Your objects are now much more active. Next, we move to encapsulation. This pillar teaches us how to bundle data with methods and control external access to that data. Without encapsulation, objects are just simple containers. With it, they become robust, secure components that protect their own data state. Let's explore how restricting access and validating inputs makes your objects reliable and professional. Our fourth pillar is inheritance. the mechanism for passing traits from a parent class down to child classes, much like family DNA. It is a powerful tool for reusing code, keeping your codebase DRY, and modeling natural relationships. The syntax is simple. Put the parent class in parentheses after the child's name. In this example, the dog class inherits from the animal class. Because of this relationship, calling "speak" on a dog works automatically without any code duplication. Children can do more than just inherit. They can add new methods, like a dog adding a bark method, or they can replace a parent's method entirely through a process called overriding. This allows for specialization. Sometimes you want to add behavior while still keeping the original functionality. The super function allows a child to call the parent's version of a method, then add more logic on top. It is also standard practice for constructors. Inheritance is most effective when one parent supports many child classes. Here, a vehicle parent class provides basic attributes and methods for both car and bike subclasses, allowing us to define core shared logic exactly once. Python supports 4 distinct inheritance patterns: single, multiple, multi-level, and hierarchical. Each serves a unique architectural purpose, though you should always be mindful of complexity, especially when working with multiple inheritance. Consider this employee system. By using a base employee class, we keep common logic centralized. Managers and developers then inherit those features and add their own specific roles, proving how inheritance streamlines professional software design. Let's recap. We have parents, children, overriding, the super function, and the ultimate goal of code reuse. Challenge yourself with the provided exercise to build an animal hierarchy, testing your mastery of these concepts. We are now ready for our capstone project, a bank account system. This is your chance to synthesize everything we have covered so far: classes, methods, encapsulation, and inheritance into one professional, functional program. Our goal is a banking system featuring a base bank account class with savings and checking subclasses. Savings accounts earn interest, while checking accounts charge a small transaction fee, perfectly demonstrating inheritance in practice. In the code, the bank account parent manages shared tasks like deposits and withdrawals. The child classes specifically override or extend these methods to apply account-specific logic, keeping the code clean, modular, and maintainable. When we run the system, you can observe the specialized behavior in action. Deposit, withdraw, and check balance calls yield different results for different account types, setting the stage for our next topic, polymorphism. Take a moment to review this architecture. You can extend this project by adding transaction logs, account numbers, or transfer capabilities. Building on a solid, inherited foundation makes scaling your software much easier.